So I am Mazgarul Islam. I will be your graduate mentor throughout the whole training session, including my other members that will be mentoring you or teaching you or trying to actually give you some lesson based on depending on the topic. So today actually I will discuss introduction to electronics and basic circuit theory. So let me actually ask you, begin by throwing a question. So how many of you know the basic structure of atoms? Like how many of you have heard about electrons, protons, and neutrons? So yeah, like I think most of you have heard about it. So as we all know, like in an atom, like there is a nucleus in the center, right? There is a nucleus. So inside the nucleus there is what? Neutrons and protons. So these protons have like positive charge inside in them, and the neutrons are basically neutral. That's why they call neutrons. However, in the outside of the atom, outer layer of the atom, electrons are another charged component which have the same charge like the protons, like similar amount, but they're negative. So that's how an atom is completely balanced, like same amount, same charge of protons inside and same amount of electrons outside. But what about if we create an imbalance? Think about it, like if we just evacuate an electron from the outer shell, what will happen? So there will be an imbalance of charge, right? There will be a vacancy of electron. We can say that there is a redundancy or excess of positive charge. So we can say that we actually call it ion, but you can just call it a positively charged entity. Like there is more proton, then there is more electron outside. So that's actually how a positively charged atom is formed. Besides that, the evacuated electron, think about it. How many of you know that like at Coulomb attraction have force or electrostatic force? How many of you have heard about it? So electrostatic force or Coulomb attraction force is basically nothing. If you keep a positively charged and negatively charged particles like nearby, they attract each other. Okay. And if it is vice versa, if there is like similar charge, like negative or positive, they distract each other. They don't attract. So what happens is if a electron is evacuated and it goes to a nearby atom, the nucleus of that atom tries to attract it. You see my point? So in a material, there are like countless atoms, and if let's say electron evacuating from one atom goes to another somehow, I'm just giving you an idea. So that nucleus of that atom will try to hold it. You see? But what about if the electron has so much energy that it doesn't actually care about the nucleus attraction? What will happen? It will cross the nucleus, cross the atom to atom to atom. You know what will happen? The electron will travel from one atom to another atom to another atom to another atom. So what will happen is electron will act like a traveler here. Electron will be basically a traveler. So that is called a free electron. When an electron actually can deny or can overcome the attraction force or the other forces around to travel from one atom to another atom to another atom. And then this way, traveling of electron happens, and we actually know it as the electricity or the current. So I'm just trying to give you an idea of that. So as I've already discussed, like the different types of like charges, they attracts, and if they have similar charges, positive, negative, they don't attract. They distract each other. So yeah. So what happens is, let me give you a brief, like in this way, actually, electricity is created. Sorry.
You just said here. There are different materials. Some of them are conductors, and some of them are isolators, insulators, or dielectrics. The conductors, they have lots of the free electrons he's talking about. That's why we call it conductors. because lots of free electrons, they are moving everywhere. With the dielectric materials, the atom keeps very close tied to the electrons, very close, as if there is a mother and tying to her kids, they wouldn't let go. Same thing with dielectrics, they wouldn't let electrons go away. So there is no free electrons, so there is no current in dielectrics. Dielectric means air, means glass. There is no current to go through those materials. But if you get metal, copper, gold, aluminum, there are lots of free electrons on those metals. So there is material conductors, there are materials insulators, and there is somewhere in between, which we call them semiconductors. It depends on the temperature. Sometimes they become good conductors, and some they become very poor conductors. And everything depends on those free electrons he's talking about, that they keep jumping from one atom to another and so on.
Yeah, thank you, Professor Fatih, for the wonderful explanation that he has just now given. So as he has said, the traveling of the electrons freely among atom to atom to atom actually is not available in all kind of materials that you see. For example, if you just look at this wood, electron actually cannot travel freely. It is kind of a insulator. It's not a good conductor. So what are good conductors? Like you have heard about it, like metallic wires that we use, for example, like copper wires. How we have an abundance of free electrons. We are getting like a lot of free electrons inside. That's why actually we can flow electricity from the copper wire relentlessly. But we cannot do the same thing by a insulating wire, like the paper, like columns. We cannot do that in that materials. So depending on the abundance of that free electron, number of free electrons, we actually classify them in several materials like dielectrics, conductors. There is another interesting material that you will learn through this session is semiconductor, which falls somewhere in between conductors and insulators. So this. Yeah, so now I will talk about potential, electron potential. So what is potential actually? So potential is basically, think of remember, I was trying to discuss something like when we actually remove an electron from, let's say, an atom. You see, there is a positively charged created, positive charge created, it is an atom with a lack of electron at the outer layer. So what will happen? It will remain as positive charge. So as I said, let's say you bring another electron nearby. What will happen? It will attract it, or it will travel spontaneously to the atom if you don't give any resistance to it. Like it will travel. So this is something what potential decides. Like potential decides, electric potential is something that decides where the electron is attracted and will travel spontaneously. So let's say if you have two let's say cylindrical water container and you connect them. So if I ask you like in which direction water will flow, actually if you look at the water level inside, let's say the containers are transparent, you can easily say that, right? Like the water will flow from the left container to the right container through the connectors. Why? Because for the water, height actually decides water will flow in which direction, right? So this is the height. Why? Because of gravity and other stuff, which is another scope of discussion. But what I'm trying to put here is like the water height here. Actually, water height here is actually deciding which directions water should flow through the connector, right? In electrostatics, in similar manner, actually, electric potential decides in which direction electrons should flow. For example, if in a wire, if I ask you the electron should flow from this direction to this direction, how the electrons will know that? Because electrons will know that which direction is the lower potential. So it will always travel from higher potential to a lower potential. for example, every one of us actually use a battery, right? So without a battery, none of our devices works, right? We have remote controls, we have like wide variety of devices in our home that depends on electric battery. Why without connecting a battery, there is no electricity or there is no, it doesn't work. Why? Because there is no device inside without the battery that creates the potential or telling the electron, okay, flow in this direction. How will electron inside them? Like no, like let's say if you like this device, it has metallic wires inside, right? But if I don't actually connect a battery, it will not work. Why? Because free electrons are there, but they don't know which direction to flow, for example. So when I actually connect a battery, I am actually creating 2 points, and I am actually creating 1 point higher potential than the other. So electron will know, okay, since this is the higher potential, travel from this direction to this direction. So electric potential will tell the free electrons to, where to move.
But let me again say it in a different way. You always the opposite attracts. So if you look at the battery, there is positive and negative. If you put it in a circuit, then the electrons would right away try to go to the positive because they want to be neutralized. Meanwhile, if the positive charges would go to the negative charges. And you start to see current, which is going to talk about that there would be flow of charges. What happens is in the material, you heard about those free electrons. They are moving everywhere. But if someone can guide this flow of electrons in a certain direction, then you are going to create a current. Like you go to a movie theater and everyone is coming out. If there is no one to come and tell them, this is your time to go, then it will be very nice flow of people coming out, exiting the movie theater. The same thing, you have the material, you have lots of electrons going everywhere. Once you put the charge, the battery, which will going to tell the electrons will go this way, you will define the flow. And that's what we call it. You create a potential difference, which you create the difference in pressure, for example, in those water pumps. So similar in the circuit, we create a flow of electrons by putting positive and negative, then electrons will go to the positive. Even with always, all the time, we say about electrons moving to the positive, but electrical engineers decide that really the current is opposite of the electrons. So when you say a current, it is really the positive going to the negative. Even we know it is electrons is the one who is moving, but the notation we're going to use, that's always positive to negative. But it is just electrical engineer decide we're going to watch for the positive charges. Even we know whatever is moving is the electrons. Why we talk about why the electrons are moving? Or we always say there is current coming from them. The electrons are very light compared to the atom itself or the muon. Those are very, very heavy. You have very light, very small element, which is the electrons. So they are much more easier to move in one thing.
Thank you for the wonderful explanation. But I was just going to try to explain the same concept, but I think Dr. Fatih has covered a lot of it. So as he already explained that you have seen, so it can also be explained in a way, in a fashion like a negative charge electron. Since electron is a negative charge particle, it actually is distracted from here and begins to flow in the opposite direction. And since positive actually attracts electron, it begins to flow in this way. But electrical engineers, they have actually decided to keep the conventional current flow in the positive to negative direction. That's why you can see that we have a flow at this direction. So when a battery is connected, what you should remember for as in this same class, I will discuss how we solve several circuits, how we will measure the currents and stuffs. You always remember that the current will flow from the positive terminal to the battery to the circuit, and then all the way to the circuit, through the circuit, to the negative end of the battery again. So current will flow in this direction always. From the positive
Again,
terminal.
the definition of the current is movement of the positive charges. Even we know it is movement of electrons, because electrons are much easier to manipulate. It's much lighter. That's what the positive charge, all of the electrons would go to the positive side.
Thank you. So now I will just show the symbol of the conventional symbols of voltage source, or what we call batteries, and sometimes we don't call it battery because there are different types of electric potential source. So throughout the whole training session, from now on, we will refer the potential difference as voltage. So and the left of the leftmost symbol is basically a single battery. You will always remember a single battery, and the amount of voltage or the amount of potential difference that that particular battery creates will be somehow maybe written with it if it is given. If there are several batteries are connected in this fashion, for example, do you remember any device that you have connected several batteries one by one after one? There are like torchlights that we used to use before. Or there are like some devices that we have, like we connect one device after another, one above one. So this is the second most figure is basically the same assembly. We are connecting positive terminal. This is the positive terminal of the battery, and this is the negative terminal of that battery. So let's say we connect another battery here, the positive terminal here and the negative terminal here. We connect it subsequently. Why we do that? We actually want to create bigger voltage difference or bigger potential difference. So for example, this battery has a 3-volt battery, let's say. So what this does is create a voltage difference of 3 volt between this node and this node. If I connect another 3 volt here, what will it do? It will create another voltage difference between this node and this node. You get my point? So if I connect three batteries, then there will be 9 volt of voltage difference from the beginning of the first battery and the end of the last battery, or the positive terminal of the first battery and the negative terminal of the last battery. Do you get it? Like, do you have any question? Please. Yeah, sure.
Can't you determine the direction of the current even if it doesn't tell you based on whether or not the voltage is negative and the direction you measured it? So, like, if it doesn't tell you when you're measuring the direction of the current which way to go, does it matter which way you go, or can you determine that after you finish measuring the voltage?
Yeah, very good question actually. So in a circuit, you actually most of the time you need to actually have a certain direction of the current. For example, you are just concerned about in a circuit, you just concerned about, let's say, a component, electric component, an LED. You have connected an LED. You want to measure the current across it. So you know that okay, how much current it can flow. So you only measure it with an let's say an ammeter. There is a measurement device. You calculate the current. You don't care about the direction there. You only care about the amount. But let's say you want to solve a circuit. For actually solving a circuit, you will see this in this class actually. If I can cover all the topic before, you will see in this class that if you want to solve a circuit, you must know the direction of the current. And most of the time, if you have this kind of battery, you will assume and this is the actually right direction, that current will begin from the positive terminal of the battery throughout the circuit and will come back to the negative terminal of the battery. You need to assume it before. There can be exception because there are other voltage sources that might be involved, but typically we will assume that one. I don't know if that have answered your question.
No, I don't.
Can I add something? If you pick the wrong direction for your current will come out negative.
It's negative.
Yeah, don't you just flip the sign? If it comes out negative, the difference is still the same though?
So let's
Can't
say,
you- does it-
let's say what he's trying to say is, sorry for interrupting. Let's say you have assumed this direction of current. So when you actually solve the circuit, when you solve the circuit, keeping other principles as they are, you will find that at the end the current value will come as negative. Then you will know, okay, my the value I have got is in the reverse direction that I have assumed. So you will know that okay, current is actually flowing towards this direction. If you assumed it the other way, that you will find the current at positive something. Like
In
this.
other words, if you are talking about resistance, which is a circuit component he's talking about, it really doesn't matter the current go this way or go the other way. But some components that we will know, it is important for us to know which direction is the current. So we have to design the circuit to give you a current going in a certain direction rather than the other. So knowing where is the current going to go, which according to our notation is positive charge going, is very important because of those elements that is very important to get the current in a certain direction, not the other direction. And at some point we'll be talking about diodes, for example. Diodes will allow current to go this way, wouldn't allow to go the other way. Yeah, so it's important to know direction of the current.
Yeah. Thank you for the explanation. So as I was discussing, like we will use these symbols for our subsequent like discussions. Some textbooks and some of the lessons that you will also see this symbol, which also actually have the same meaning as this one, like V. There are another type of voltage source that you see here, which is AC voltage source. So this is a different type of voltage source. We do not call it a battery. This is alternating current based voltage source. What it is basically is, so the battery that you typically use, like a typical Duracell battery, it has a reading. If you anyhow read the battery, you will actually know it's written actually back of the battery that how much voltage or how much potential difference it gives. So if you have a 9-volt battery or 3-volt battery, you will know okay, it will always create a 3-volt voltage difference. Okay, and that is constant throughout the time. It will remain as a 3-volt. But what about the voltage sources that we use for our appliances typically? For example, you see the socket, like the voltage sources around here. We connect it with our laptops, we connect it with our iron machines, everything, right? What kind of voltage does it give? We actually do not call it battery if you think about it. This is basically another kind of voltage source, which is alternating voltage source. It doesn't give us a constant 9-volt voltage source, a constant 5-volt, constant 3-volt. It gives us something like this, a sinusoidal voltage or alternating voltage. So typically this voltage source in US, it gives us 110 volt like peak. So for example, from 0 it goes to 110, it goes back to 0 again, minus 110, something like that, which you don't have to worry about for now, but I'm just giving you an idea like what type of voltages do we typically need in our daily life. So that is what we will call AC voltage, and the batteries and constant voltage we will call it DC voltage, direct current. So DC and AC. So typically for the AC, the symbol is pretty straightforward. It already tells you what kind of voltage source it is. So it's kind of AC, and this is DC voltage source. So if we plot, for example, with respect to time, so if we see that with respect to time, a DC voltage source gives you the same voltage over the period. You see, like if you have a 9-volt battery, that will give you 9 volt throughout the whole day, for example. But for AC voltage, it will actually give you this kind of alternating. There will be 0 volt, then 110 volt, let's say, then minus 110 volt, then 0 volt. And how much time does it actually oscillates? Like gives this kind of ripples or this kind of how much time does it really alternate in a single time cycle? For example, here we have probably, if I'm not wrong, 60 hertz of AC signal. What does that mean? What that means is the voltage actually gives us 0 to 110, then minus 110 and 0. This cycle is repeated 60 times in a single second, which we call frequency. See, so that's that particular source have frequency of 60 hertz. That means this alternation happens 60 times. So can you imagine? Like it's quite high too. So so what is current flow? So as Dr. Fati has given a very good explanation, like current flow is basically the flow of electrons, free electrons through the like conductive element or other element. So for example, in a conductive wire, like a copper wire or any other metal wire, electrons actually flow this way. These are like traffics in a highway. You can imagine it like this way, traffics in a highway. So not only we give a voltage there. If we give a voltage, it doesn't tell us that okay, current will generate. Okay, so current is another very crucial parameter that actually measures the travels of electron. How many electrons are traveling? It's not potential difference. So for example, you have potential difference of 9 volt and 1 electron is traveling, 2 electrons is traveling. I'm just giving you an example. But the same potential difference can actually make thousands of electrons or billions of electrons actually to travel this way. This actually depends on another parameter, which is material dependent parameter. I will talk about that later. But how we actually measure the current? So for example, if you have a wire, we imagine a plane and we calculate how many electrons are actually crossing this plane per second. Do you get it? Like we measure the current in this way, how many electrons are passing. So for example, I am a traffic controller here. I am ready with my gun, like a speed gun, and I am measuring how many cars are traveling, crossing me, like this. Like current basically tells you how many electrons are traveling through that particular hypothetical plane that we are imagining. So the more electrons are flowing, the more current it flows. That we say it this way. More current. If someone says more current is flowing, that means the higher number of electrons are actually crossing that particular plane. So we actually measure it in the number of charge. So each electron actually has a specific charge. Actually, this is basically 1.6 into 10 to the power 19. I don't know if actually you have heard about it. There is a specific charge that each electron has, which is specific for every electron, and that is 1.6 into 10 to the power 19 minus 19. That means 0.190 then 16 or 20 sorry 20 then 16. Do you like get it? So this is a very tiny amount of charge, but remember, only one electron is not flowing. Billions and trillions and exillions electrons are flowing through a wire. That's how we get a measurable current. If let's say one electron was flowing, the current was too low and we could not even measure it, right? There are billions of electrons are traveling through a wire. That does actually it gives us a measurement in the instruments.
So the unit of calculating the charge is called a well-known scientist. His name is Coulomb. So it's a charge would be measured by Coulomb. The charge of electrons is very, very small. And he said something 10 to the minus 19 over Coulomb. Very, very small. Coulomb is huge, but we're going to call the charge of electron the E, which is the charge of electron 10 to the minus 19.
Yeah.
It's very, very small.
Yeah. So yes, that's the what actually current is. So current is basically in mathematically how we measure it. It is basically the charge that has crossed the plane divided by the time that we considered for the charge to pass. For example, if you have like 3 coulomb of charge, let's say passing through within 3 seconds. For example, if someone has informed me, okay, throughout this plane, 3 coulomb of charge has passed. 3 coulomb charge means huge number of electrons, as I have already discussed. And I have counted 3 seconds for this 3 coulomb to pass. Then the current will be 3 coulomb divided by 3 seconds. 3 by 3 will be 1. And what is the unit of current? Unit of current is ampere. So if I ask you, what is 1 ampere of current? 1 ampere of current is basically if per second the number of charge, the amount of charge that has passed through this plane is 1 coulomb in per second, then we will call it 1 ampere. Okay. Do you have any question?
So I like his description of the current as a flow of cars. Someone standing by the traffic and he's counting how many cars will go through this interface, this cross section. And he will say, how many cars per second? And he will tell you this is very heavy traffic or it's very low traffic. Depends on how many cars per second. The same thing we do here. If there are lots of electrons going through in very small unit of time, then you have to say, I have high current. That charge, the units is called, that charge of time is seconds. So coulomb per second is our other unit, which is ampere. Ampere is another scientist. Yeah, then we called it coulomb per second is ampere.
Thanks for the explanation. So these figures actually tells you what we actually think about low current. It is really like sparse, and this is really dense. So this is just an illustration to show you how high current and low current, what does it really mean.
So what does it mean for us? If it is heavy traffic and I want lots of number of cars, what do? We expand to many lanes, right? The same thing with current. If it is lots of electrons, high current, I want to have thicker, bigger wire to carry all the current. If I don't have much current, I can have very narrow, very thin wire to carry this number of electrons. So the same concept.
Yeah. So actually, let me ask you about like, let's actually see how you have understood it. So let's say I have 90 coulomb of charge flowing through this plane in 10 seconds. What is the amount of current? 9 amperes, exactly. So let me know if any of you actually have still confused about how to calculate the current on charge and time. I think everyone is clear, then I can move to the next slide actually. So far what we have learned is basically two very vital electrical parameter, that voltage and current. So we see that voltage actually tells you like which direction to flow and actually give you an amount. And how much voltage is basically decides how much it pushes the electron. But the amount of current that flows through the wire actually depends on another very crucial and important parameter, which is known as resistance. So what is basically resistance? So let's think about something. Let's go back to the highway analogy. So think about office hour at 5 p.m. You have come out of your office and driving towards your home. Isn't there a lot of traffic outside at 5 p.m.? You cannot actually drive at 70 miles per hour, right? Because there is a lot of traffic. On the other hand, let's say you come out at, let's say, 2 p.m. You see that highway is really, you can actually drive at 80 miles per hour. That's not a problem. In the same highway, I'm talking about the same highway. You can go very fast or you can go really slow depending on the things around. This is what I am trying to explain is basically resistance. Resistance is something that actually defines the hindrance or obstacles that electrons feel while they actually travels through the metallic wire per se or any other materials. So when electron travels from one atom to another atom to another atom, I have already said the nucleus is trying to attract them. Not only that, if they come across another electron negative and another electron is negative charge, they repel each other, right? Or some electrons collide with each other. There are a lot of hindrances, there are a lot of obstacles that electrons have. Like you driving in the highway, you have a lot of obstacles. You have a lot of trucks, big trucks that going on, right? You have a lot of other cars. You collide sometimes. So this is something. These kind of hindrances also exist for the electrons as well, and we collectively call all of these obstacles as resistance. So there is not a single source of resistance, by the way. Resistance has a wide variety of sources. For example, electron is repelling another electron, pushing another electron. Sometimes in some materials there are like atom level phonons, which also like I don't know if I will be able to cover it, but there are some other sources of resistance as well. We collectively call it resistance for a measurable quantity, for actually finding so that we can measure. Okay, someone tells us, okay, this particular metal has a resistance of this. Someone says, no, this has twice the resistance. We will know, okay, electron will find struggle to travel in this, then more in this. You see? So resistance is basically how much electrons have to struggle to flow. You see my point? Do you have any question on that?
So let me try. Imagine the material is made out of not good conductor. I like to think of it as many atoms in the material, and this flow of electrons is trying to get by. If they are very crowded, then it's very tough for the electrons to go through, because there are lots of obstacles, lots of problems to go through. Like you have lots of barriers in the road and you are trying to drive, you try to go around, so it is harder to travel along this route. That's one way to think about it. But if it is conductor, really there are big distance between those atoms. So the flow is fast. So what is stopping it is how many free electrons. The minute you put potential difference, which is a voltage, lots of free electrons would go to the positive side of things. So we say this material has low resistance. We just allow everything to go through. If it has more free electrons, it will have very high flow of current. Just waiting for this voltage difference to allow them to go. They were moving before, and the minute we put voltage difference, they start to move around very fast and have this flow. So the resistance of the material depending on if it is conductor and how many electrons there, and then if it is really not good metal, what is the characteristics of the material inside, and those atoms, distribution of those atoms inside as well can affect the resistance of the material. This is very important element for us, or characteristic for us, the resistance of the material. There's a crazy guy who started this by saying, I have a battery and I want to measure the current. So he was able to measure the current. He started to change the same material, change the diameter, and see what happened to the current. Then once he measured different diameters, he said, okay, I'm going to change the material. One time I'm going to use aluminum, one time I'm going to use copper, one time I'm going to use gold, and so on, and see how much current on the other side. And that's what he started to talk about, that he's going to measure the resistance by ohms, and he's going to describe it.
Yeah. So thanks for the wonderful explanation. So in the circuit level, we will use this symbol. So basically, as you know, like if something wants to travel, like it cannot. This symbol actually says that it is a resistance. So how we measure the resistance is basically so in the previous slides I have discussed that typically we consider voltage, like the volt as the unit of voltage, volt, and we consider ampere as the unit of current. For the resistance, we consider ohms, which is basically which is basically symbolized at Greek letter omega. Oh, there it is. So, are you familiar with the Greek letter omega? So, this is what we typically write as the unit of resistance. So, this is just able to remind you of the three most important parameters for analyzing basic electrical circuits. Or not only basic electrical circuits, all circuits, these are the basically three most significant parameters that you need to know. Voltage, current, and resistance. The unit of voltage is volt, and unit of current is basically ampere that I have discussed, and resistance is this Greek letter omega, which is pronounced as ohms. So there is one scientist who actually invented a law which actually relates these most three significant parameters: voltage, current, and resistance. How are they related? So how this ohms terms came, actually that particular scientist's name is basically Ohm. So he invented this law. That's why given on a tribute of his name, the unit of resistance was given his name ohms, and the law is called Ohm's law, which actually unifies these three different most significant parameters. So if you give a voltage, the voltage is related to the current and resistor. But basically, these three are related to each other by this formula. So this is very simple formula for all of us. We must agree, right? But you should know that this is basically the foundation of electrical engineering, the Ohm's law. So voltage is basically the multiplication of current and resistance. Or if you think about it, current is the division of voltage and resistance. So you can think of it this way. If you give a voltage, so think about the second formula here. Current is equal to voltage divided by resistance. So think about it. I have two different materials. Okay, I am giving the same voltage, but since another one of the material have higher resistance, it will have lower current, right? If you think about it, because I equal to V by R. So whichever materials have higher resistance will have lower current because resistance is divided. So if you give the same voltage, doesn't mean you have the same current, right? As Dr. Fatih has already described, there are several types of materials: conductors, insulators, semiconductors. These are classified based on their resistance. Remember, based on their resistance, material resistivity or resistance. So if a material has very low resistance, then if you divide something of a very low quantity, for example, if you divide 10 divided by 0.1, what will you get? 100. If you divide 10 by 100, what will you get? 0.1. So what you are dividing actually dictates, like in the same voltage, how much current it will generate.
So this is very important experiment. Many of the discoveries started by working on the lab. Someone is doing some experiments out of curiosity, and he wants to see what happens there. And he does it so many times and sometimes for many years. So this is a good example of this guy had a wire and come up with a battery. And he was measuring the current. And he said, okay, what happens if I double the battery? Instead of one cell, I'm going to do 2 cells. And he found out once he doubled the battery, the current is double. Okay, let me do it again. Instead of 2 cells, I'm going to make 3 cells. He found out that the current is 3 times. Kept doing that and found there is kind of simple relationship between the voltage and the current. It's a constant, which we call it the resistance, which is V divided by I gives R, always constant, no matter what. When he doubles the voltage, he doubles the current. Triple the voltage, triple the current. So always the ratio between the voltage and current is constant, which we call it the resistance. And out of respect for this guy who invented very important law in electrical engineering, and his name is George Ohms, we called it Ohm's law. And even the unit of resistance is ohms. Because of this guy who spent years observing that. Then he said, okay, this is for this material, let me try another material. And he found the same thing. And that is always constant. V divided by I for this material is the same constant. It's different from aluminum, it's different from copper, it's different from gold, but it's always constant. That when you measure the voltage, measure the current, is always constant relationship. So his next question, how do we calculate this resistance? Is there a way to predict this resistance? That's what we're going to talk about. But always the ratio between the voltage and current is constant over an element which is called the resistance. Because there are many other elements. Okay, there are inductance, there is capacitance, there is a diode, there is a transistor. Those are all the components in electrical engineering. Now we're just talking about the simple element, which is the resistance.
Thank you for the explanation. Actually, that actually sums up a lot of the ideas. So this is a triangle that you can simply keep in mind so that you can remember very easily. So the relationship between these three parameters are kind of visually given here. For example, if you want to get the current, think about it. You have voltage divided by resistance. You see, if you want to get the resistance and you have voltage and current, you have the voltage divided by current. If you want to get the voltage, you have the current multiplied by resistance. So do you get it? What the picture is trying to help you in a visual basis. So basically, if you want to find the voltage, you see where the current and resistance are side by side. How we typically write it in mathematics? Multiplied, right? IR. So V equal to IR. What is I? I is basically V on top of R. You see? What is R? Or resistance? Resistance is basically V on top of I. So this is just a visual aid to help you to remember how these three things are related. So this is basically what I was to do. If you want to find the V, it is IR or I into R. I is basically voltage divided by resistance, and resistance is basically voltage divided by current. So as Dr. Fatih was describing, you have the same material, but you are increasing the voltage by connecting another battery. So if you connect two batteries, you are seeing that current is twice. If you connect three batteries, the current is increasing also 3 times. So you are seeing that the division between the voltage and current remains the same because it depends on the materials. See my point? So that the resistance remains constant. That significant parameter defines the material, how much current it will flow, how much free electrons there are inside. So now I will actually familiarize you with this particular thing for actually help you to a next step. Maybe in the next class I will bring a simple breadboard and resistance physically, which you can actually connect and measure it yourself. Okay, but for that before there was this kind of convention that people have to keep a lot of things in mind. There was no internet, people actually have a lot of practices that they used to do for accelerating their experiments and stuffs. So this is what it is called resistance color code. So resistance color code is basically a shortcut way to know what the value of the resistance is. And I will actually give you some resistance in the next class. You will see these are really tiny sometimes. Sometimes they're really tiny. So if something is written, sometimes it is not actually visually very feasible to see. Okay, how many ohms? Okay, I'm giving glasses. So you see what the point is? If you just inscribe it with colors, then it is easily seen. You can easily see it. And depending on the colors, you have different resistances. So there will be 4 different colors of bars. The first 2 colors is basically the first and second digit. For example, if you have red and black, you see first the red digit defines 2, and you have black, but the black defines 0. So first 2 digit, red and black means 2, 0. Okay? And then the third color bar is basically a multiplier. So how many zeros will you add? If you have 2 digits, then how many zeros will you add after that is defined by the third color bar, which is multiplier. Multiplying by what? How many hundreds or thousands or 10,000? You see my point? So what is the multiplier there? Green, the third color, look at the green. So green is basically 5, and to multiply in the third color, it's 10 to the power 5. That means 5 0. Add 5 0 with it, or multiply 10 to the power 5 with it. Do you have any question on that? Are you clear?
So what's the tolerance?
So yeah, there is another color, which is an inevitable question. I think many of you already have that. So this is basically tolerance. Tolerance is basically how much resistance it may vary, like how much resistance variation it can be. So for example, you are manufacturing a resistance, right? You are manufacturing resistance in an industry or in a lab. You are precisely given to manufacture, let's say 112 ohms, or let's say 12,000 ohms. You see 12 kilo ohms. There might be a little variation. So how much? So that is this tolerance actually signifies. So the fourth color actually tells you how much tolerance it has. So the fourth color is basically gray. If you look at gray, the tolerance is 10 to the power. Oh, so tolerance is I'm sorry. My bad. I actually forwarded it a long time ago. So tolerance is basically just have 2 color options, gold and silver. If it is silver, it is 10%. If it is gold, it is 5% of mismatch.
So what happens is the guys manufacturing lots of those, producing many of those, and then he takes a sample. So he's producing thousands. He takes a sample of those and start to measure the resistance. You would expect that all of them would be 2 megahertz, 2 mega ohm, for example. But because of the manufacturing errors, variation could be plus minus, goes up and down, up and down. And we define them either between 5% variation, or if it is bad, it's 10% variation. If it is more than 10%, either he will sell them very low because it became 20%, 30% tolerant, which is bad, or he will stop the production and readjust the machines to get to 5%, 10%. So what we are trying to tell you, even you are asked for 2 mega ohm, you will not get 2 mega ohm. You will get 2 plus minus 5% or plus minus 10%, which your circuit, your design should be okay within that. But you have to check for this sensitivity. Is it that sensitive or not? Hopefully it is not. There are variations. Suppose you want to say, no, I want to have 2 meg because my design tells me it's 2 meg. Otherwise, it will not work. You have to pay more. Okay, because I'm going to get all this lot and start to select. I will spend time testing for those fancy exact resistors to go. So it's going to cost you money. That better off to just to buy off the shelf those components and live with the 5% tolerance or the 10% tolerance. Otherwise, if you start to look for more tolerance, you have to pay more.
Thank you. Thanks for the explanation. Sometimes it just stops working. Oh, so this is what so there was one slide which I will explain later on, which is basically depends this is an hour. So this is a very basic circuit, and so here what we have done, we have connected a battery, not a battery actually, several batteries, okay? A series of batteries, as I have already discussed, to increase the voltage. So for example, you need a 24-volt battery, but you go to the market and you see that there is no 24-volt battery, but you have, let's say, 6-volt battery. So what you can do, you can just buy 3 of them. Buy 3 6-volt batteries and connect one after another. So if you connect 4 6-volt batteries, how much voltage will it generate at the end and the beginning? 24-volt, right? So that is what sometimes we do in circuits. We just augment one after another to create large voltage. For example, here 24-volt. And here this voltage source is connected with this resistance. Now, if I actually give you the voltage and the resistance, can you calculate me the current, given the current? Think about it. So basically, we have the relation between voltage, current, and resistance, right? So we can easily calculate from the voltage for the triangle discussed, right? So if you have 24-volt, I have given you the voltage. What is it? 24-volt. And what is the resistance? Do you remember the resistance?
12 ohms.
It's 12 ohms. So 24-volt with 12 ohm resistance. So what will be the current? 24 divided by 12, which is 2 amps. So in these 3 parameters, any 2 are given. If I give you any 2 of these parameters, you can easily calculate the other third one, right? That's what I was trying. Okay. Here. So as you can see, they calculated. So just for your exercise, you can just begin calculating this and let me know within a minute, probably. You can do it in pen and paper, or you can just do it in your mind, whichever you will feel comfortable. Just to make sure that you clearly understand the relation between these 3 things.
Very important for us to know how much current. One simple reason is what is the diameter of the wire I'm connecting the battery to the resistance. If it is huge current, then I need to have wider, bigger cross section of the wire. If it is low current, then maybe just simple wire would do the job. So this is a very important task for us. There are many wires with different diameters, and you have to be able to carry the capability of those wires. That's exactly when you design a highway. How many lanes do you want? You have lots of traffic, you have many lanes, which is wider.
Are you done? So, who is going to tell you what's the value of the current in the first circuit? Yeah, go ahead.
3 amps.
Yeah, that's exactly right. Thank you. Who is going to tell me the voltage at the second circuit? Yeah, sure. The second circuit.
Second one on the bottom or on the right?
Oh, I see. You did this one. Yeah, excellent, excellent. I was confused. Yeah, thank you. It is exactly right. Who is going to tell about? Yeah, go ahead.
13.
So now I think you just got the pretty basic idea of what the relationship between these three significant parameters. Let me ask you something. There is a mistake in this, in all of these three circuits. Okay, tell me about it.
The current's flowing.
Exactly. Do you get it? So there is a mistake in all of these three circuits. As Dr. Fatih has already discussed, we are not considering the flow of electron as the direction of current flow, which is quite the opposite, right? We are thinking. So always remember that the current flow direction is from the battery, from the positive terminal of the battery toward the resistance. Quite often, you will need to know in a bigger circuit that which direction of the current is flowing through the resistance. So if I ask you, what is the direction of current through the resistance? You will tell me, okay, from this terminal, this side of the resistance, to this side of the resistance. And let me ask you something. If I ask you, what is the voltage difference between these two terminals? This is relevant for next, actually. Yeah. If I ask you, what is the voltage difference between these two terminals? It's 8 volt. It's given, right? So, which of these have higher voltage?
The one on top.
The one on top, because it is connected to higher voltage, and it is connected to the negative voltage. Right? Positive terminal is the higher voltage. So I can say that throughout the this resistance has a voltage of 8 volt from this terminal to this terminal. So this is at a higher voltage and this is at lower voltage. We already discussed that current will flow from higher voltage to lower voltage. So as you have already figured out, the current direction is wrong here. So current direction is this way.
So in our notation, we say negative current. If you look at the direction will come this way again, you found out it's wrong, you just say minus 10 ampere, minus 10 volt.
Yeah, excellent point. Actually, I forgot to actually mention that. For example, if I, in your exercise, I gave you this circuit. I gave you this circuit exactly as it is. So instead of coming here and complaining about the direction of current in the question, so for example, you have found out, okay, the value of the current is 3 amps. But you are telling me, okay, you have actually put the question wrong. The current direction is quite the opposite. No, you will actually give me an answer of minus 3 amps of current. Because I have specified what I want. I want the current from that direction to that direction. So you will give me the current is minus 3 amp to tell me that the current direction that you have given is actually the opposite of what the current actually is going. You know, that's what Fatih has explained. No, actually, this is what I have already discussed. So these are some units of measurement that will come in handy when you will actually move to the subsequent discussions. And a lot of those you already typically hear in your daily life, right? If you do computer, if you buy computer hardwares, if you have your mobile memories, everywhere you will find this kind of measurement units, which you will need a lot as well when actually doing like mathematics in or circuit analysis. So you have heard about like megabyte, terabyte of memories. So we often use the term mega, kilo, milli, right? This kind of measurement units. You must need to know what this typically means, because people will not tell you, okay, I have a voltage source of 1 divided by 12. People will not tell you that. People instead will tell you in your question, okay, I have a picoamp current in my circuit. You don't know what pico is, you will not know that, okay, how much current is going, you know. So for this kind of to avoid writing a lot of zeros and avoiding mistakes, people have actually come up with these short terms for these measurement units. Same goes for the higher power as well. For example, if 10 to the power 12 means 12 zeros after 10, right? So this is basically called as tera. So you have heard about terabyte of memory, like modern hard disks are terabytes. So now you should know how many bytes are in there. It's basically 12 zeros after 1 and then bytes. So if I tell you, okay, I have a resistance in a circuit which is 1 mega ohms or 1 kilo ohms, you will have to know what mega ohm or kilo ohms means, which is basically how many zeros you have to put in your values, right? So try to learn this. You just Google it, like measurement unit table, you will know. So typically there are a lot of shortcut methods to keep those in memory, like picoterms. There are a lot of rhymes. You can also learn that as well, but you must need to know few of them actually. For example, 1 megahertz means 160 after that. I think escape these things. Okay. So now I will talk about the equivalent resistance. Let's think about it. Fatih was discussing something on the like highway analogy. Like if you have a materials, these have a resistance, right? So for example, you want to increase the resistance of the highway. Like you want the traffic to move more smoothly and more speedily. What will you do? You are a construction worker or you are a policymaker. You will actually extend the lane, right? Make the roads more wide. Same thing can be done for the electrical wires as well. You can make these wires more wider to electrons to flow smoothly. And think about it, just a question of intuition. If you increase the thickness of a wire, do you increase the resistance or decrease the resistance? Decrease the resistance so that electrons can move freely. Now, if you decrease the thickness of the wire, you increase the resistance on the other hand. Now, let me ask you something. If I just connect or if I just increase the length of the wire, not touching the thickness at all, what will happen? So let me tell you, like if you have a very long highway, 25 kilometers, or if you have a 5 kilometers of highway, which have more resistance? Obviously, 25 kilometer one, right? Because you will find more obstacles in a longer highway, right? Same thing happens for the resistance as well. So you can either, so when I tell you, okay, you have this material, increase the resistance or decrease the resistance, you can do two things. You can either play with the length, you can increase the length or decrease the length, or you can play with the thickness. You can increase the thickness or decrease the thickness. If you increase the length, it will increase the resistance. If you decrease the length, it will decrease the resistance. Simple. On the thickness, it is otherwise, because thickness actually, if you increase the thickness, it will decrease the thickness. Now, think about it. For example, I have given you the materials to increase the resistance, but you cannot play with its thickness. You also cannot play with its length. What will you do? You cannot change it at all. So what you can do, you can actually connect another resistance with it. So electron has to travel through both the resistance, right? So the resistance will increase. Did you get the intuition? Do you any of you have any question?
Let me try to say different way. I have big cars. I have lots of cars. They are going to the highway. I know if I have one lane, I'll have problems, right? So what do? We have many lanes on the highway. And some cars will go here, some cars will go there, and so on. So in this case, which is the one to the right, I will put many lanes in parallel. So I have high current. This current will be distributed in those different lanes. So I have R1, R2, R3, R4 connected in parallel, like different lanes on the highway. And that they will go from point A to point B. The other one to the left, I have high voltage, very high voltage. Can I put it in one resistance? If I put in Y resistance, it will be very high current. Voltage divided by R1, I will have high current. I don't want that because each resistance has maximum current it can handle. Maximum number of electrons can go through. So what do? Okay, let me split the voltage into R1, R2, R3. Each one of those resistors will carry certain voltage. It would be I have 1 kilovolt. This is quarter, this is quarter, this is half kilowatt or kilovolt, for example. So I can distribute the voltage over those resistors. This is a simple way to look at it. We call this to the left, they are connected in series. The one to the right, they are connected in parallel or in shunt. And those are very common for us. Okay, we'll show you what we call the equivalent resistance. To the left, you just add the resistance R1 plus R2 plus R3 plus R4. That's the equivalent resistance. So if one is 1 kilo ohm, 2 kilo ohm, 3 kilo ohm, the sum, the equivalent is 6 kilo ohm. I'm just adding the values. If they are connected in shunt, then there is another formula which is 1 over R1, 1 plus 1 over R2, 1 over R3 is equal to 1 over R equivalent. So this is series connection, this is shunt connection. And one to the left, what is common between R1 and R2, R3? What's common? What is common between R1, R2, R3?
On the left?
The one in the left. What is common between the three resistors? They have the same? They have the same what? Current. All of them, they carry the same current I. That's right? Same current will go through R1, R2. The same number of cars will go through R1, R2, R3. That's right? Each one will have a different voltage, what we call it voltage drop. The voltage drop at R1 is I, R1. The voltage drop at R2 is I, R2. The voltage drop at R3 is I, R3. So they have different voltage drops, but they have the same current, I. They are common in the current. If you go to that, one to the right, what do they have in common? Voltage. It's a dual, okay? That the voltage between A and B is the same. But the current at the first lane is equal to the voltage divided by R1. The voltage in the second branch is V over R2. The current in the third branch is V over R2. The current on the fourth branch is V over R4. So each branch of those will have different current, but all of them will have the same voltage. The one to the left, all of them, they have the same current. The one to the right, they have the same voltage. And if you know the voltage and you know the resistance, you can calculate the current in each of those branches. Okay? So the bottom line is if the resistors are connected in series, we just add the resistors. If the resistors are connected in shunt or in parallel, we add the reciprocal of those. 1 over R1 plus 1 over R2, 1 plus R3 is equal to 1 over R equivalent. This is like the basic for electrical engineering. When you talk to any electrical engineers, listen to what he says: current, voltage, resistance, current, voltage, resistance. They are connected in series, they are connected in shunt. That's what all.
Thank you. Thanks for the very elaborate explanation. So I just want you to take the one of the figures like this one, like Dr. Fatih has already discussed. For example, just connect one of these things to here. Like as I was trying to give you a visual explanation, which Dr. Fatih has already said. So the same electrons will flow, right? The same electrons will flow. You have two resistance, for example, in series, one after another. You will have the same current. That's what is explained very well. And on the other hand, for example, you have created another lane in parallel for the same electrons to travel. Then will be the current same? No. The current will depend then on their specific resistance, which I will discuss in the next slide. Yes. So what is basically equivalent resistance? Equivalent resistance is something you will need to calculate the overall circuit parameters and behaviors and stuff. For example, in the left circuit, you see that the resistance are connected in series. So as Dr. Fatih has already said, just add those up. Just add those up, and you will find an equivalent resistance. So equivalent resistance is something, for example, you replace all three of them. You just start all three resistance and replace all of them by only one resistance. What resistance is gonna be so that the current will be the same. That resistance is basically the equivalent resistance or total resistance. You see my point? So if I tell you, okay, I don't want three resistance, I want only one resistance, so the current will remain the same. This is basically this summation. Same here. If you want to replace all of these parallel resistance by only one single resistance, so that the overall circuit current doesn't change, it is basically this equivalent resistance, and this is the formula. So if I give you a several assembly of series and parallel connected resistance, I hope you can calculate it from these two formulas. Yeah. So I am giving you some values of the resistances. Just let me know what the equivalent resistances are. I think it will give you a, like, let's say it's 8 ohms, it's 2 ohms, and it is 10 ohms. I am just so what will be the equivalent resistance here? Yeah, thank you so much. So let's say, for example, here it is. Oh, it's creating some trouble, so I just. So for example, it is like 100 ohms. It is 200 ohms. It is 50 ohms, and it is 25 ohms. Let me know what the equivalent resistance is for this assembly for this. Yeah.
375.
375 for this one?
Yeah.
Okay, anyone else?
One,
For the one on the right.
how did you get to that?
Didn't you say we're supposed to add them?
No, we didn't say that.
Yeah, think about it. Like, you need the value of Req, okay? So what you will do, you will just create 1 by Req. 1 by Req. My pen doesn't work for some reason. Okay. Yeah. So what you'll do, you'll just write this equal to 1 by 100 plus 1 by 200 plus 1 by 50 plus 1 by 25. So if you just do a simple mathematics, you will see that it is gonna be around 200 by 15, something like 15 by 200, which is basically how much? 3 by 20, something like that? No, 3 by 40. So REQ, what is the, it is 1 by REQ. So you have to reverse it again. So REQ will be 40 divided by 3. So if you calculate it, it's gonna be around 13.33. Yeah, 13.33 ohms. Sorry for the bad handwriting. It's because my pen is not working. I am writing by mouse. Do any of you have question?
So again, this is for the one to the right. Now,
Yeah. So what about the left one?
we don't we don't add values, we add the reciprocal of them.
Yes. So 1 by REQ is basically 1 by the reciprocal summation. At first inverse them, then sum them, then inverse them again. Keep in mind. What is the result of the leftmost circuit here? So it's basically very simple. Yeah, 8 plus 2 plus 10, which is how much? 20. So the result is 20 ohms. Now, actually, let me give you a very brief intuition here. So look at the value of the resistances in the right circuit: 100, 200, 50, 25. So see the values. Now see the results. What is the equivalent resistance? 13 point something. You can see that the equivalent resistance is lower even than the lowest of them. You see my point? If I tell you what is the lowest resistance among these, 25, the result is even lower than that. So if I give you any circuit to calculate an equivalent resistance, when you get the result, check it. If you see that, okay, my equivalent resistance is actually in a parallel assembly coming bigger than some any one of those, you are wrong, definitely wrong. Your equivalent resistance in a parallel assembly, in a parallel connection, will always be lower than the lowest of them, even the lowest of them. Now come to the left circuit here. Here, what is the result? 20. Simple, because you are adding them up. Obviously, the result will be bigger, even the biggest of them. So, in a series assembly, the result will be bigger than the biggest of them. In a parallel assembly, the result will be lower even from the lowest of them. See my point?
So give them a few minutes and say the battery is 5 volts. Can you guys tell us what's I1, I2, I3, V1, V2, V3 for both circuits?
Yeah.
Please, you guys start.
Yeah, you can do that now.
I need to know the current in each resistor, the voltage of each resistor, if the applied voltage is
5 volt, right? So I'm writing it down for you. 5 volt here. So what you will need to know, you will need to know, calculate the current. Okay.
current in each resistor, voltage in each resistor for both cases.
Are you guys done?
We're not giving grades. We're open discussion. You can
Yeah.
make mistakes, no problem. We're learning, so we're allowed to make mistakes.
I think this one. Thank you. This side, yes. You know. Oh, yeah. I think you need it. Like this. No, actually. Thanks for trying. Are you guys done? So, who is gonna tell you what's the total current of the left circuit is? Yeah, go ahead.
0.25 amperes.
Yeah, excellent. So if you want to calculate the overall current of the left circuit, you calculate the total resistance first, which is 20 ohms, then divided by voltage. 5 divided by 20, which is basically 0.25 amps of current. Now, who is gonna tell me what is the voltage? Let me rephrase my question. What is the voltage across 8 ohm resistor, the first resistor? What is the voltage across it? Or what is the voltage difference of the two terminals of the 8 ohm resistance? Yeah, sure.
3 volt.
3?
Yeah.
So how did you calculate it?
I just did it by the difference. So, like, because if
So you multiplied the resistance value with the current. Oh, actually you did the right way, but the result is wrong. 8 multiplied by 0.25 should be 2, right? So it will be 2 volt. Did you get it? Let me actually draw it down for you. So the total current comes here is around 0.25 ampere, okay, by amps. Now, what is the voltage difference between this node and this node? What is the resistance? 8 ohms. And what is the value of voltage difference is equal to the current that is flowing into the resistance. Now, what is the current flowing that we have calculated? 0.25. So multiply 0.25 with the value of the resistance, which is 8. We get 2 volt. So what is the voltage difference here? 2 volt. Now, in the same way, who can tell me what is the voltage difference across the second resistor, which is 2 ohms? Yeah, go ahead.
0.5.
0.5 volt, excellent. This will be 0.5 volt. And what is the voltage difference in the third one? 2.5 volts. Excellent. So the voltage difference here is 0.5 volt. And voltage difference here for the third resistance is 3.5. Oh, sorry, times 2.5. So it is basically,
Yeah, should be on the same idea.
yeah, excellent. So it's gonna be 2.5 volt, okay, in this third resistor. Now let me ask you, just add all the voltage drop here across these three resistance. 2 plus 0.5 plus 2.5. What it becomes? 5 volt. You see my point? So all the resistance in a circuit, if you sums up all the voltage drops across all the resistors, you will know what the value of the battery is. You see my point? Which is 5 volt. If it doesn't match, then you will know, okay, I have miscalculated. At least some. You see my point? Now, can you do a similar analysis or similar
So this is not
calculation?
similar to, I have $5. I have 3 kids. The older, which is R3, will take most of the money. He took 2.5. The middle one, which is the 8 ohms, took second highest. So he took half. The third one, which is the youngest, was easy to please because it's only 2 ohms anyway, so I could half volt. So that my total is 5 volts. I cannot exceed the 5 volts. So I'm going to split them, but not equally, depending on their height, depending on their age, depending on their resistance. It will start to distribute the voltage. Yes, sir.
Wouldn't the electrons eventually get out of the resistor? Like when they collide with the atoms in it, wouldn't they eventually all come out?
Yes.
Like at some point?
But in order to do that, there will be some heat generated. If it is high current and you have lots of current going through, they will collide, there will be some friction, and they will generate heat. And that's what we are worried about. That's why we widen the cross section. Once they go through this resistance, we love to have no resistance at all. It will be flawless flow. But because of the resistance, you will have some heat generated because of the friction between the electrons.
Thank you. So just now I want you to do a very similar analysis in this circuit. So for example, what I'm doing is I'm actually connecting a battery between these two terminals, which have a, let's say, how much should I give? 100 volt. Okay. Did you get the question? I'm just connecting this A terminal and B terminal with a battery, which has 100 volt of voltage. Now, what I want you to do, I want you to measure the current across each of these resistance. I1, I2, I3, and I4.
So deep in your mind, you are always thinking, what can I measure when I go to the lab? Can I measure voltage? Can I measure current? Can I measure resistance? And that's what you guys are going to learn. At this point, we're just showing you how to do calculations. But eventually, you will need that once you go to the lab. That you'll be able to measure our basic quantities, voltage, current, resistance.
Let me know when you guys are done. If anyone wants to tell me the values of the current levels, let me know. Like I1, what are the values of I1, I2, I3, and I4? So who wants to tell me the values? Anyone? Yeah, go ahead.
I got one for the first,
Yeah,
and then do I keep going or?
I think anyone else want to tell me the value of the I2?
0.5.
0.5, excellent. What is the value of I3? Yeah, it's basically 2 ohms, and I4 is basically how much? 4 ohms. So yeah, excellent. So as you already have the idea how to calculate the current across a parallel assembly like that. So the values are basically you multiply the voltage difference between these two resistance divided by the value of the resistance. For example, here the voltage difference, all of the voltage difference across all of the resistance is same, since their terminals are connected in the same node, right? The same terminal. So they have all 100 volt in their two terminals, but they have different current because of their resistance values, right?
It's nice to look who got the most of the current. The 100 ohm or the 200 ohm or the 50 ohm or the 25. 25, the smallest one, got most of the current, right? He was able to get 4 amperes, 4 amperes. The rest, like the first one, got 1 ampere. Second one got 50, half, and so on, 100.5, and so on. So the smallest resistance got most of the current. All of them have the same voltage, but if it is small resistance, it will absorb all the current. Imagine this resistance is 0. What will happen?
The circuit would burn out.
Yes, what we call this? We call it short circuit.
Short circuit.
We call it short circuit because it's going to have voltage, which is 100, divided by 0, that means it is infinite current. It's going to take all the current you have and it will burn because it's able to handle this infinite current because it has finite radius. So what we say, oh, I shorted the circuit. I made it a short. That means I put very low resistance on R4. So it became a short circuit. On the other hand, if you look at the one to the left, I have 5 volts. And who got the highest voltage? Who got the highest voltage? 10. The 10, the biggest, right? Imagine I want to open it. R3 became open. How much of the voltage would be?
If you cut the wire like these two and make it open. Okay.
How much would be the current? If I open the circuit, no current will go through. It's infinite. I mean, voltage divided by infinite value, it's 0. I open it. There's no flow. It's open, no flow. So in this case, we say the circuit is open. I mean, you put a voltage, you're trying to see if there's a current in the loop or not, but there's no current. That means it is open circuit. So we have two extremes between you short circuit the circuit by putting short circuit, 0 resistance, or you open the circuit by having infinite resistance in the series connection. Those are the two extremes, either short or open. The other thing you learn from this exercise is in order for you to have a current, you have to have a closed loop. Must be a closed loop. If it is open somewhere, no current whatsoever. So you need to have a closed loop for the current to go. Those are basic things we learned from this simple example.
Thank you. So another thing that I would like to imagine a hypothetical circuit now for this parallel assembly here, which doesn't have all the 4 resistances. Let's think about it. Just omit all the resistances in this parallel assembly and replace it with only one resistance, which is the equivalent resistance that you calculated previously. What was that? Do you remember that? 13.33, or we can write it simply 40 divided by 3, or you can write it 13.33. Now think about it. We have a 100-volt battery and you have a resistance of how much? 13.33 or 40 by 3, whichever way you prefer to write. Now it has a 100 volt. Now, can you calculate the current in this circuit, this hypothetical circuit?
It's 13.33 ohms or ampere.
If someone calculates it, it's going to be how much?
7.5.
7.5 amps. Now do one thing. 7.5 amps. Now going back to the previous assembly, add all these currents. What this becomes?
7.5.
7.5. You see the point? So equivalent resistance is something that you can just replace without altering or changing the total current that is coming from the battery. You see? So basically, what is the amount of current that is going through here, entering? 7.5. You see? And this 7.5 amps current is basically dividing between these 4 lanes of these 4 resistance. And are they dividing equally? No. Some of the resistance are taking 2 amps. Another one is 0.5 amps. Why this division of current happening? Because their resistance levels, that's what Fabi was explaining. Did you get it? So what you will do in this kind of circuits, if I tell you to calculate the total current, you don't have to calculate 4 current, by the way. If you can just calculate equivalent resistance. What is the equivalent resistance? and divide the voltage by the equivalent resistance, you will note the total current. If let's say I have not asked you the current through all of the resistances, you don't need to do 4 calculations. Let's say I have hundreds of resistances. Will you calculate hundreds of them? No. You just calculate equivalent resistance and then divide the voltage by the equivalent resistance to get the total current, which is basically 7.5 amps. So as we have seen, the current is basically divided between this parallel assembly. Let's come to the series assembly that I previously discussed. Here, the same current is flowing, right? 0.25 amp current is flowing through all of these 3 resistors. But instead of current being divided, here the voltage is being divided. Do you see it? I have already discussed it. Like the first one is taking 2 volt, second one is taking 0.5 volt, and third one is taking 2.5. So here voltage is divided instead of the currents. So in a series assembly, voltage division happens, and in a parallel assembly of the resistance, current division happens. Current is divided in a parallel assembly and voltage is divided in a series assembly. Yeah, so this is an exercise that you can try here, I think, for calculating the equivalent resistance. For the top 2 circuits, you don't have any voltage source. I am just asking you calculating the equivalent resistance only. There is no voltage source, so there will be no current. But if I, let's say, connect a voltage source here, you see the 2 red bubbles. If let's say I connect the voltage source, what will be the equivalent resistance of the overall circuit? The full circuit. Go ahead and try it. And please ask me right away if you find anything confusing there. So let me give you some tips. At first, try to know which resistance is connected to which resistance in series and which resistance is connected to what in parallel. If you have confusion on that, you will not be able to solve this actually. I will actually explain the overall process to do that, but at first I want to give you some time. Think about it. Are you guys confused? Let me know. Like, please feel free to ask question and feel free to make mistakes. Yeah, sure.
Yeah, so I think, can you explain it one more time how to solve it?
Yeah, sure. I think so in any if you ever come across any of these a little bit complicated circuits, I must tell you that you cannot do it all at once. You have to make step-by-step progress to actually solve the circuit. Like the previous one, it was really straightforward. 4 circuit in parallel or 4 circuit in series. Resistances in series or 4 resistances in parallel. Here in this complicated circuit, not all of them are parallel with each other, not all of them are series with each other, right? So reduce the resistances little by little. Okay, so let me actually give you the brief overview. Like, see these 4 ohms, these 5 ohms, and these 3 ohms. They are in series. Can you see that? Like after the 4 ohm, 5 ohm, then a 3 ohms are connected. So we can just replace these 3 resistance by one single resistance of how much ohms? 4 plus 5 plus 3, right? Any confusion in question? So what we are doing is we are reducing little by little. So these 4 ohms, these 5 ohms, and these 3 ohms are in series. So what is the equivalent resistance of series? Just add those, right? So 4 plus 5 plus 3, how much it becomes? 12 ohms. So there is a 12 ohm resistance like this. Then these 4 ohms, this is basically like this, right? So now, can you see they are parallel? So what you will do now, you will reduce or replace these 2 resistance by a, oh, by the way, rest of the circuits are still there. I am not drawing it because it's really hard to draw in mouse right now. So they are still there. But now can you see these 4 ohms and 3 ohms, 12 ohms are basically parallel. So what I will do, I will replace those 2 resistance by their equivalent resistance. What is the equivalent resistance of parallel assembly? You have a formula, right? Do you remember the formula? Like 1 by R equal to 1 by 4 plus 1 by 12. So what you will do, you will calculate 1 by 4 plus 1 by 12, and this is 1 by equivalent resistance. Now, if you calculate it, you will find it that the equivalent resistance is basically 3 plus 1, 4, 3 ohms. Okay. So if you calculate it, you will find it that the equivalent resistance of this assembly is 3 ohms. Let's replace it by 3 ohms. Do you have any questions so far? So I am replacing the 4 and 12 ohm resistance by a 3 ohm resistance. Then there is a 3 ohms, there is a 6 ohms. Okay, there is a 3 ohms. 3, 4. Okay, now this is the circuit. So can you see we have reduced the circuit quite much? We have actually made the circuit much smaller. We are not there yet. We are still on the process. So can someone tell me what's the value of this resistance is 3 ohms, right? We have just calculated. These resistance are the series or parallel? Series. So you can just erase these 2 resistance and connect one equivalent resistance. And what is the value of the equivalent resistance? 3 plus 3, 6 ohms. So what I will do now, I will erase this, and I will just connect a 6 ohms, right? Now, you see these 6 ohms and these 6 ohms, are they series or parallel? You see my point? These 2, they are parallel. So now calculate the equivalent resistance of 6 ohms. 1 by 6 plus 1 by 6, which will be
3.
Which will basically be 3 ohms. If you calculate the equivalent resistance of this, you'll find that the equivalent resistance is basically 3 ohms. So let me erase those again. Ohms. Now, can someone tell me what's the next step?
Series.
Yes. Now you can see that
10.
these 4, these 3 ohms and these 3 ohms, they are in series. How much that is? 10 ohms. Any of you have any question? Because this is really important. If you want to solve circuits in the subsequent sections, you have to really understand it really well. See? So, any of you have any question? So, what's the equivalent resistance of that circuit? 10 ohms.
Yeah.
You see? Now, please solve this one, the second one. Because this way I will know that you have understood it. For example, equivalent resistance between this terminal and this terminal. And once again, once again I must tell you, you have to solve it step by step. Reduce as much as you can. Then you will be able to solve it. Okay. So 2 10 ohms in parallel, then 1 10 ohms in series, and then these are parallel again. 25, 10, and 20. Please try to solve it and let me know the result. And always, when you reduce the circuit, check it by intuition if your results are correct. For example, this is a parallel assembly. If you reduce it, your resistance here, only this part will be even lower than 5 ohms, right? I've already discussed it because it's a parallel assembly.
5.5.
Yeah.
And stand and then back again. Just a side question. Just a side question. So when you solve it, do you draw the circuits every time, or what? Do you draw the circuits every time when you solve it, or is it a shortcut?
That is something that, for example, for now, I will advise everyone to draw it because, for example, let's say for this circuit, I will ask you in this circuit later, maybe in the next class, probably, that what is the voltage difference here? Then, when you have reduced its circuit to 2 steps, each of these steps will be helpful for you to calculate separate calculations. Yeah. If I ask you just only one question, for example, what is the equivalent resistance? There's a single question. You can either do it by your head. You don't need all this stuff. But sometimes for complicated circuits, each steps can be helpful for you. So big calculation.
Another just a follow-up question. So is there any sequence, like, like when you solve the equation, you have a sequence, you do this.
That is an excellent question, actually. For example, always remember, this is a really good question. Did you understand what she asked? So she asked that if there is any direction that I should actually prioritize for beginning the reduction process, I reduce my circuit, right? So you see, what is my equivalent resistance here in these 2 terminals, right? in these two terminals. So try to begin at the farthest point, if possible. Not only that. If you see that, okay, farthest point is difficult, then try to, let's say there is another resistance here. I'm just giving you an example. You can just erase these two resistance by only one, right? But the equivalent resistance, you can begin here as well, but always try to be in the farthest point. So when you reduce it, it comes to the terminal that was given for you, right? You will know it actually when you practice enough.
Yeah, but for this one, it's fine. You can just go.
Yeah. This one, it is fine. It is, you can begin here, it's same. So who wants to give me the number or give me the result? Yeah, go ahead.
17.
Excellent. Did you get the same result? 17.5 actually is the right answer. Yeah. So so basically 10 and 10. And one thing I must tell you that there is a very shortcut. You can either keep it in mind or you can just ignore it. For example, what's the equivalent resistance of these two terminals? 5. Always remember, you have two resistance. Each of them have same value 10. Just divide it by 2. 10 by 2, 5. If you have 10 ohm of resistance, you can just divide it by 3, 10 by 3. You don't have to do the math all the time. Sometimes having the same value actually helps to, you know, make it just a shortcut. So let's say if you have 550 ohms, you basically erase them by 50 by 5. 10. Okay. Just you can either keep it in mind if you want.
I think there will be time for break.
Yeah. 1 o'clock.
So we can have your lunch. Now it's getting serious now.
Yeah.
So are we going slow or going fast? Need to tell us.
Yes.
Do you need more examples or less examples? What do you want?
You practice this.
Is that?
You practice this little.
So you guys want me to give you a few more exercises so that you can practice to actually move you. Okay, I will actually draw some circuits now. Try to draw it as clearly as possible because my
So it's a homework in the classroom that.
yes. So what I will do, I will give you a little bit more complicated circuit, which is not complicated if you look at it this way, but probably in the same assembly here, I will just add a battery. You will tell me what the voltage and what's the current across each of the resistance. Okay, I will draw the circuit for you to give you as a homework.
Solving the third one.
No. I am giving you a completely new circuit. I will draw it.
So how long we have break? What time to come back?
I think it's here. So everyone is here.
Yeah.
I think so. Okay. So at first, actually, I want you to guys focus on this particular circuit. Next answers. Otherwise, I don't have this. So this is the circuit that we will actually together solve this. But before that, I want to actually explain some of the formulas. Formulas not already the concepts you already learned, but I want you to actually learn something that will actually give you the idea to readily solve it in a very fast way. Otherwise, you have to calculate the overall current, then current like equivalent circuit seconds, a lot of the process. So which is called as voltage division. So if you remember, like in one of the series connections, you saw that the voltage is basically divided between different series resistances, if you remember it now. That's okay. That's
If you want the answer?
no. Just just keep it. Don't keep it. No.
Okay, so is it?
Yeah.
I'm good.
I can see the voltage.
That. Right? That is a good choice and we can think. I think it's. I think. It's all those classes. Okay.
But it was 100 volts. But I think it's fine. That's why. What is it?
It was 100, but I think he's going to increase it.
Oh, yes. Yes.
Easier for me. Yeah, but you
But you can.
So you are pretty right now. You are actually pretty familiar with this assembly, right?
Yeah.
So if I ask you, okay, what is the voltage across this resistance? You can easily calculate it, but you can actually calculate it in 2 steps at least. You just calculate the equivalent resistance first, and then divide it by the voltage, right? To get the total current, and then multiply the total current with this resistance to get this voltage, right? So actually there are 3 steps if I think about it. There are actually way where you can just following one step do that, and that will come in handy when you actually solve bigger circuit. So think about it. If I ask you what is the equivalent resistance here? Equivalent resistance is R1 plus R2 plus R3, right? And what is the total current here? V by R1 plus R2 plus R3. Do any one of you have any question about it? Like any confusion? Since you know the total current now, what is the voltage across this resistance? Are you guys still with me?
Yeah.
So what? Since I tell you this current is flowing through all of the resistance, right? Series, they are in series. So what is the current flowing through R2? I, same I that I have just calculated. So what is the voltage difference here, which I can call, let's say, VR2? VR2 will be basically the current that is flowing across it into R2. Any question? If I now replace the value of I from here to here, what I will get? I will get V by R1 plus R2 plus R3 into R2. Are you guys with me? Yeah, we can write it in a very interesting way, which is R2 divided by R1 plus R2 plus R3 into V. Can we not write it this way? They are basically the same, right? So, do you see a pattern? What is the pattern? All the resistances in the denominator, and only the resistance that is under consideration is in the numerator. R2 divided by R1 plus R2 plus R3 into total voltage. Are you guys with me? So if I ask you, okay, what is the voltage here? What you will do, you write it this way. R1 plus R2 plus R3, all the resistance, and above in the numerator, just only write R1 and then multiply it by the voltage. Then you will get the voltage. You don't have to actually calculate the current, then multiply it with the resistance. This is called the voltage division formula or voltage division rule. Sorry.
You get the voltage or
To get the voltage across it.
you multiply with voltage?
Sorry. Yeah, here. And this will be the resistance across the R1. You get that
What's on the left? Is it I1?
here?
Yeah.
Oh, I think. Oh, it is basically the VR1. Sorry for the VR1. Are you guys following? Please let me know if you have any question. It is something that it will just really help you, and you don't have to memorize or anything. Just plug it in and solve it. So let me ask you something now. Can you see the board? Because I think both of them now. Now, only use the voltage division rule to calculate the voltage across this resistor, and this resistor.
Is it 20, 10, and 20?
20, 10, and 20, yes. Oh, I have to write it. Only use voltage division rule. I know you can do it by calculating current and stuffs, but only use this formula. Can you do it?
It's just everything multiplied by 2.
Okay, so what is the voltage difference across this resistor, which is, let's say, VR1? This will be basically
40.
all the resistance 20 plus 10 plus 20, and only this resistance. What is this resistance?
20.
20, and then multiply it with
50. Now multiply is 100.
100, which is basically 20 by 50 into 100, which is basically 40 volt, right? Any confusion? Same way, what is the voltage here?
20.
Yeah. 10 by 20 plus 20. You see the point, right? So it will be in the numerator, it will be this resistance divided by all the resistance. Any confusion? And this will be 40 as well. So the overall voltage difference that you will find is 40 volt here, 20 volt here, and then 40 volt here. If you sum that up, it should be 100 volt, right? 40 plus 20 plus 40. This is voltage division rule, which sometimes give you a little bit easy way to actually solve circuits like this, like the circuits I drew at the beginning. So let's solve it by voltage division rule. Okay, you don't have to calculate all the currents. So I will show you how. So most of the time when after actually a particular period, most of the time you can actually solve a particular circuit in a few ways actually. So if someone wants to actually solve this circuit without the voltage division rule, you already know how to do it. Calculate the total current and stuff. Now let's solve this circuit. Okay. So to solve this circuit, let's actually try to reduce the circuit a little bit so that it comes to our understanding. Now there are series, parallel, series, then parallel, a lot of this stuffs. Either keep all of those series or keep all of those in parallel. Then you will actually can solve it. So let's replace these two resistance by equivalent resistance. What will it be?
10.
10. So 1 by 20 plus 1 by 20 equal to 1 by R. So 1 by R equal to 2 by 20. R equal to 20 by 2 or 10 ohms. So we basically can replace these two resistance by 10 ohms. So what will so there will be 100 volt. There will be 10 ohms. Then there will be 5 ohms. We cannot reduce it anymore. Then 15, 15, 15. What will be the equivalent resistance? 5. 15 by 3, which is really easy. 5 ohms. Then we have this smaller circuit, right? Which is basically represents this circuit. Now, let me ask you, if I now tell you what is the voltage across this two node, this is the voltage here as well, right? Because we have reduced the circuit here. So the equivalent resistance does not change the voltage across here. That's why it's called equivalent resistance, right? So what is the voltage here? Voltage division rule. Follow the voltage division rule. 10 divided by 10 plus 5 plus 5, okay? Into total voltage. What will it be?
15.
50 volt. So now we know that, okay, the voltage difference between these two nodes is what?
50.
50 volt. What is the voltage here? What is the voltage here? Same. Right? Which will be 5 by 10 plus 5 plus 5. 10 plus 5 plus 5 into 100, which will be 5 by 20 into 100, how much? 25. So here the voltage difference is 25 volt. Okay. Any confusion? What is the voltage difference between this node and this node?
25 volts.
Excellent. So basically here as well, 5 divided by 10 plus 5 plus 5, which is basically 25 volt. If you calculate it, find it. Within these two terminals we have, let's write it here, 25 volt. And for a sanity check or for fact check, what is the summation? 50 volt, 25 volt, 25 volt equal to 100 volt. If you sum these up, it should actually give you the total voltage. You got the point? Now, this particular at this stage actually you have everything. How? You can actually tell the voltage difference across each of the resistor. Already have it. What is the voltage across this resistor? 50 volt. What is the voltage across this resistor? Same. They are connected in parallel. If they are connected in parallel, they have the same volt, right? Here as well, they have the same 25 volt. These three all have how much voltage across them? 25 volt. You see? Now, if I ask how much current is flowing through each of them, you have the voltage across them, you have their resistance value, you just divide the voltage divided by resistance, you get the current. What is the current flowing here? Only this resistor. 50 volt divided by 20 ohms. Okay. Any confusion? So the current that is flowing through this resistor is 50 divided by 20, which is basically 2.5 amps. So here it is flowing 2.5 amps. What is the current that is flowing here? Same, 2.5 amps. Excellent. What is the current that is flowing through here? 25 divided by 5. 5 amps. What is the current that is flowing through here? 25 by 15, right? Which will be Anyone? 1.67, right? 1.67 amps. 1.67 amps. 1.67 amps here as well. Here as well 1.67 amps. So we get the voltage and currents across each of the resistors, right? Easily. Any one of you have any confusion? Now, 2.5 amps and 2.5 amps is summation is being added up here and becoming 5 amps. This 5 amps is dividing again 1.67, 1.67, 1.67. You sum this up, you will get 5 amps. You see, current is being divided in the resistors. Now, let me tell you what is the current here. What is this? How much? Anyone? What is the current that is evicted from the battery? That is getting out from the battery. What is the total current? Remember, the total current is basically getting up from here and dividing it between these two resistors, right? You can just add these two current, then you will get the total current. Or you can think of this way: whatever the current here is, what it must be going through this resistor, because this resistor doesn't have any parallel path, right? All the current must go through this. So the current is 5 amps. So here it must be, this current must be 5 amps. Any confusion? Please let me know if you have any, if you are thinking that, okay, I'm not. Now, I want, this is the, I think, last exercise that I want you guys to do yourself here. It's basically the same, probably very similar. I just want to make sure that you understand that. So what you need to do, you need to actually get the current of each across each of the resistors. It's really easy calculation. It should not take you that time. Go ahead. At first, reduce the circuit. So let me tell you. At first, reduce it like this. Reduce it like this. Okay. Then you will know what is the voltage across the resistors and what is the current. Are you guys being able to solve it? Or finding it tough?
What is point C?
Oh, that's just the name of the point. Ignore it.
Oh,
There is nothing here. Like, for example, if someone asks you what's the voltage difference between the point C and point D. So basically, as you can see, DEF is basically the same point. And sometimes when you draw the circuits in simulators and softwares, they actually name the nodes automatically. So basically, it's this name of the point. That's it.
We are teaching you the hard way, but eventually there will be some software that you will use, mix it.
How are you guys doing? Are you guys okay?
Yeah, you guys have 4 graduate teaching assistants and 2 undergraduate teaching assistants. Use this, okay, in a nice way. Don't abuse them, but use. So if you have questions, ask them to help. That's why they are listed.
What are the 2 URAs? You know,
So we have 2 undergraduates that are actually seniors, and they did everything we're talking about. I might have some freshmen at UT joining us as well.
Are you guys done or not done? Think about it. Always, if in any circuits, okay, like this, like the previous one, try to make the circuit smaller. Okay? Like I have done here. So as you can see, this is way too complicated for me. Okay, what I have done, I have just reduced these 2 into 1. Reduce these 3 into 1. Do you remember? So that the voltages across this resistance remain the same as this one. Okay, and that is simple equivalent resistance problem. So when you get the voltage, you just divide it with the resistance value, you get the current across each resistance. That's it. It's that simple. For example, you just calculate. So, do any one of you have any confusion about these 2 resistance are in parallel?
No.
Any one of you have that confusion? Like these 2 are parallel, right? They're basically same node. If there is no component, nothing new, and they're connected, they're basically same point. Okay. So these 2 resistance are parallel. So you just use parallel resistance formula, and 1.2 by 1 divided by 2.4 plus 1 divided by 1.7. I don't know what it comes. You need to use calculator. Then what is the equivalent resistance of this assembly? 1 by 60 plus 1 by 20 plus 1 by 30. It's gonna be 1 plus 3 plus 2, which is gonna be 10. So this assembly will have an equivalent resistance of 10 ohms. And this will have something like, I don't know. It's about
it's 1.995.
1 point something. So just now
Just 0.
you use the voltage division rule to calculate the voltage across each of them. You only have 2 voltage, right? Here between these 2 points and these 2 points. What is the voltage?
11
What?
by 11, like 1 plus 10. Wait, no.
Yeah, something like that. Something like that. So when you have the voltages here, you just divide the voltage by the resistance. Then you will have the current across each of the resistance, which what is required in this question. Did you guys get it? Please let me know if you don't understand, because it is crucial for the next part in the next lecture. Okay. I can personally come there and solve
What
it.
was the formula that you were talking about?
Okay. That is the formula of equivalence resistance. For example, you see there is one. Here. So there is two resistors, right? One is 2.4, one is 1.7, right? So what you need to do, you need to replace these two by only one. And what will be the resistance value? That will be, use this formula and find what the value of R is. It's something, I don't know, 1.4 or something, I don't know.
In like 408 or
1.408. 1.408. So now replace these two by only 1.408. You see?
This one. Oh, both of them?
Yeah. So what you do, you need to just, let's for example, erase these two between the same terminal. Just use 1.4.
No, I have like one. We didn't get
Okay,
1.4.
now for the same way, similar way, do this. Replace these three by only one. And what will be the value? 1 by 20 plus 1 by 60 plus 1 by 30. It will be 1 by 10. Then replace it, it will be 10 ohms. So you will only have two resistors. When you reduce the circuit, your circuit will look like this. 1.408 plus 10 ohms. Okay. So you have this circuit.
It's not the value of the first one, it's not 1.4, it's 0.999. So 0.9, you can see it's like 4. Almost
Something like that.
almost 1. Yeah, if, but it's
0.99.
yeah, 0.99.
Okay. I don't have the calculator. That's why I asked you. No problem. So it is 132 volt. Now can you calculate the voltage across them?
So the first
When you
one,
get the voltage here, you are not actually calculating the voltage in this circuit. You are calculating voltage here actually. This is basically for your calculation. This is not the circuit I have given. This is a simplified circuit. This is the actual circuit. The circuit will not change. You are just reducing it to calculate. You see my point? So now what will be the voltage here? 0.99 divided by 0.99 plus 10 into
32.
132. And this will be around 12 volt, right?
Around 11, 10.89, 10.9,
Sorry.
10.9.
Yes. 11. And here it will be 121 volt.
That's why.
I don't know.
I did.
Did you guys get it? Now you have the voltage here, which is 11 volt. You have the voltage here, which is 121 volt. Now, the voltage across these two, 11 volt. You know the resistance. Now you can calculate the current. You see? The voltage is basically across them is same. They are parallel. So the voltage difference is same, 11 volt. So what is the current across the 2.4 ohms? 11 divided by 2.4. What is the current across 1.7 ohms? 11 divided by 1.7.
How did you find the 11 again?
That's why voltage division rule. So you have this circuit after the introduction, right? Now you can calculate the voltage here, calculate the voltage here. Like voltage division rule, 0.99 divided by 0.99 plus 10, if there is one, add it. There is not, unfortunately, into total voltage, which is 132 volt. Do you guys, are you guys clear now? Please let me know. Same way we can actually calculate the current across each of these. So here it is 121 volt here. 121. So divide 121 by 30, you will get the current here. I try. Divide 121 by 20, you will get the current here. And divide 121 by 60, you will get the current at R3. So you will have all the current across all of the resistors. Are you guys clear now? So for your not homework actually, for your practice, I will give similar 1 or 2 circuit in the Google Classroom so that you can practice and you can show me in the next class that if you have actually solved them correctly. Not me or anyone who is instructing you, you can just show them, because this understanding is kind of really required and helpful for bigger circuits. When you have big circuit, you will have 2-3 resistance, you can immediately calculate the voltage. You don't have to calculate the equivalent resistance, current and stuff, you see. So that's why. So there is the next concept that I will discuss is Kirchhoff's current law and Kirchhoff's voltage law. These are the 2 fundamental laws of electrical circuit, two most fundamental laws. So for the interest of time, I think we can wrap up our discussion for today. I will give you similar circuits so that you can practice. And I must emphasize the practice because circuit solving is all about practice. And sometimes when you practice, you know that what to do. Like sometimes you don't need to do the voltage division rule. Sometimes you will know it by yourself by practice actually. Thank you.
Thank you. Thank you. Sorry for the morning.
If you have any question, by the
We
way,
had the resistance to come to the building.
Okay.